There are two main ways to perform hypothesis tests on the mean. The first way is to use confidence intervals, and I'll be talking about this technique in this screencast. In the Introduction to Hypothesis Testing screencast, I had this example. You really like to ride bumper cars at Elitch Gardens. They claim that the rides last 3 minutes, but you think that they have been shorting you and that the rides last significantly less than 3 minutes. We set up a hypothesis test. The null hypothesis is the mean is what they claim of 3 minutes. And your alternate hypothesis is that the mean is significantly less than 3. From a long history of ride times, you know that the variance is 0.05 minutes. As I just alluded to, there are two techniques for performing hypothesis tests. This is not just for the mean, but this is also on variance, comparison of means, and comparison of variances, and others. The first one that I'm going to talk about in this screencast is using confidence intervals and confidence bounds. This actually is not quite as common these days as the second technique, which entails using p-values. In the last few decades, the use of p-values, due to the emergence and increased use of computing tools like Excel, has become far more popular than the use of confidence intervals for hypothesis testing. So the techniques in this screencast actually aren't used as frequently as p-values in hypothesis testing, so just keep that in mind. If we plotted our sampling distribution, our random variable is y, so if we plotted y bar, if it were centered on mu equals 3, then this is what the sampling distribution would look like. It would be improbable to get a sample with the y bar value in the yellow range, and we call that alpha the risk level. For example, alpha could be 0.05. If the true mean of ride time is 3, it would be rare that we get an average of ride times somewhere down in this yellow region. In order for us to accept the alternate hypothesis, we have to get a sample average that is down in the yellow region. And if we were to get a sample average down in that region, we would accept the alternate hypothesis and reject the null hypothesis. So let's talk about how we can use confidence intervals or confidence bounds. Confidence bounds are one-sided confidence intervals. Although one-sided confidence intervals or bounds are rare, we can put together a confidence bound on x bar, the sample average, assuming that we know mu. Recall that the probability that the sample average is going to be greater than L, again here on the right we have a sampling distribution, is equal to 1 minus alpha. If alpha were 0.05, then we would have a 95% chance of getting an average in this red shaded region. We can convert L to a standard normal variable, negative z alpha, that is negative of the z value containing alpha percent to the right. And if we solve for L, the lower limit here for x bar, we get that that's equal to mu minus z alpha times sigma divided by root n. We can rewrite the probability that x bar is greater than L. We can substitute L into our expression, and that means we have a confidence bound, a 1 minus alpha percent confidence bound on x bar of mu minus z alpha times sigma over root n. So we are 95% sure, if alpha equals 0.05, that the sample average is going to be greater than mu minus z alpha times sigma divided by square root of n. If the null hypothesis is not incorrect or not false, and the true mean is mu, we are 1 minus alpha percent confident that a sample average will lie above this limit, L, which we can compute here. So this is actually L. In our case, we can go ahead and compute our statistics. We know that the sample average of 5 rides is 2.75. We're going to use a 95% confidence interval, alpha equals 0.05. We know that the variance is 0.05 from a long history of these rides. We can compute z alpha. Z of 0.05 is 1.645. And when we plug these values in to our confidence bound above, we get that there's a 95% chance that x bar is going to be greater than 2.85. In other words, this lower bound here that has 95% of the sampling distribution above it is 2.84. If the true mean is 3, we are 95% confident that a sample average will lie above 2.84. Consequently, obtaining a sample size n equals 5 of less than 2.84, that's down in this yellow region, only happens 5% of the time and is exceedingly rare if the true mean is actually 3. So our conclusion, based upon our hypothesis test, since we're 95% sure that x bar is greater than 2.84, our sample average of 2.75 is not contained within this 95% confidence bound. Therefore, it's in the yellow region, and this only happens 5% of the time if the true mean is 3. And we conclude that this is rare. As a result, we accept the alternate hypothesis and we reject the null. In other words, we can accuse Elitch Gardens of shorting us on our time on the bumper cars. Let's look at a second example. The yield of a chemical process is being studied. We know from previous experience that the standard deviation is known to be 3%. The past 5 days of plant operation have resulted in the following yields. Perhaps you are a quality control engineer with the company and you just want to do routine testing to make sure that you are not varying too much from 90%. Is there evidence that the mean is significantly different from 90%? Use a risk level of 5%. Now the problem sort of just asks, is there evidence that the mean is different from 90%? This is sort of an open-ended hypothesis test. You could be greater than 90% or you could be less than 90%. And we want to test either way. Is there evidence that we're significantly different from 90%? Which of the following represents the hypothesis tests that you should carry out? If you selected D, you are correct. The null hypothesis is the mean is 90. The alternate hypothesis is that the mean is different, significantly different from 90. That means it can be less or that means it can be greater. So we set up our hypothesis test. We can collect our sample statistics, n equals 5. If I go into Excel and compute the average of these values, I get 90.48. We're going to be splitting alpha into two tails because this is a two-tailed test. It's a not equal to test. Z alpha over 2 is equal to 1.960. We can set up a 1 minus alpha confidence interval on this scenario. We are 1 minus alpha % sure that x bar lies between mu minus z alpha over 2 times sigma over root n and mu plus z alpha over 2 times sigma over root n. So this just goes back to the screencasts on confidence intervals. We can plug in our sample statistics and our z alpha over 2. And when we do that, we get that there's a, in our case, because alpha is 0.05, this is a 95% confidence interval. We get that our 95% confidence interval is between 87.4 and 92.6. 95% of the time, our x bar, if the true mean is 90, is going to lie in this red shaded region. Now, what is our conclusion? Since our sample average of 90.48 lies in the middle of this 95% confidence interval, we can conclude that there's no evidence that the mean is other than 90, and so we reject the alternate hypothesis and we don't accept the null hypothesis, we just fail to reject it. In summary, if you are performing a lower tail test and you want to use confidence intervals, you can calculate a confidence bound using this equation. You reject the alternate if x bar is contained within the confidence bound. Otherwise, you can accept the alternate hypothesis. For an upper tailed test, you can reject the alternate if the sample average is contained within this confidence bound, a lower tailed confidence bound, x bar less than mu plus z alpha times sigma over root n. Otherwise, you can accept the alternate and reject the null. For a two-tailed test, you can set up a confidence interval, you reject the alternate, and fail to reject the null if x bar is contained within that confidence interval. And that's what I showed in my last example just a few minutes ago. Otherwise, if x bar is not in that confidence interval, you can accept the alternate and reject the null. Hopefully, this screencast gives you a better idea of how we can perform hypothesis tests on the mean using confidence bounds and confidence intervals. In the next screencast, I'll show you how we can use p-values to perform hypothesis tests, and using p-values is far more common these days than using confidence intervals. Thanks for watching.